Today we're going to be talking about adding moles of HCl to each of these solutions in the buffer lab, but it's going to be actually 0.0002 moles of HCl. This was my original intent, but I actually wrote 0.02 originally, so every one of these turned out to be a strong acid at the end. But now it's not going to be the case. So let's take a look first at the first example. I'm going to add H plus into a strong acid. And the question is there a reaction? The answer is no, there's no reaction. So then we are going to go back to the solution scenarios and understand that I have a strong acid added to a strong acid. So whenever you have that, you just want to do total molarity equals moles over liters. Now what I need to do is I need to find the original moles in the HCl from the original example. So original solution of HCl, I had molarity of 0.1, and then I had a volume of 5 milliliters, so that's 0.005 liters, and then that gave me 0.0005 moles of H plus in the beginning. So I'm going to add that 0.0005 plus what I'm adding now, which is the 0.0002, and divide that by the total volume, which is 10 milliliters, and that's going to give me a molarity, total moles of 0.0007, divide that by 0.010, and you have 0.07 molar. So now I just take the negative log of H plus, which equals 1.15, and that's going to be the pH, which is fairly acidic. Okay, in the second example, we're going to add H plus into a strong base. So the question is the reaction? The answer is yes, stoichiomoles, because it's an acid and a base that are not conjugates. So let's write the reaction. You're adding H plus into hydroxide, and you're just going to make water. We're going to do ICF chart. The moles of H plus are 0.0002. The hydroxide is going to end up being the same calculation as we did before for the HCl. So the original solution of NaOH was 0.1 molar, and it was 5 milliliters. And you're going to find 0.0005 moles of OH minus. So that's going to go right here, 0.0005. And water is not that significant for this. So the H plus is going to run out. So now you're going to have 0 of this and 0.0003 moles of the hydroxide. So now what are you left with? You're left with a strong base. So if you have a strong base, you just do molarity equals moles over liters. The total liters is 10 milliliters. The moles is 0.0003. So your molarity is 0.03. So now what you're going to do is you're going to take the negative log of OH minus. Okay, this is OH minus. This was H plus in the first example. I should have just labeled that over here. And when you do that, you're going to get 1.52, which is the POH. So then you have to take 14 minus that, 1.52, and that's going to be 12.48. And that's going to be the pH. So if we draw a quick picture of all these, at the end of the first example, all you had left in your cup was H plus. That's a strong acid. Right, so this was a strong acid we had over here. So you just did molarity equals moles over liters. Whereas in our cup over here, all we're left with is hydroxide, which again was a strong base. On numbers 3 and 4, again we're adding 0.0002 moles of HCl to each of these. So we're going to add HCl into the weak acid. First question I have to ask, is there a reaction between a strong acid and a weak acid? The answer is no. So I just look back at what I have. I have a strong acid and a weak acid, so I only care about the strong. So that means I'm going to do molarity equals moles over liters. So I need to find my original moles of HCl. So it's going to be molarity was 0.1. So, not HCl, but acetic acid. The original was 0.1. The original volume I used of that was 0.005 liters. And so my original moles is 0.0005 moles. But that doesn't really matter because I'm not going to need the weak acid anyway because I only care about the strong. So I don't need this. It's just an extra. Sorry about that. So all I need is the moles of the HCl, which is 0.0002. And the liters is 10 milliliters altogether. And so my molarity is going to be 0.02. And then I just take the negative log of H plus, and I find out that that's going to be 1.70. So there's my pH. It's a strong acid. And when I'm all done, all I have is H plus in here and HA, but the HA doesn't give me a significant amount of H pluses. So technically I would do ice, but the ice is not going to give me anything extra for the H plus significantly. Okay, the next one, I'm going to put H plus into a weak base. So strong acid, weak base. Is the reaction? The answer is yes. So we do stoichiomoles. So what's the reaction going to be? The H plus is going to react with the ammonia to form ammonium. So you're going to do this in moles, stoichiomoles, ICF. The initial H plus is going to be 0.0002. That's what we're adding in. Now I need to find my original ammonia. So I do molarity equals moles over liters. The original liters for the ammonia was 0.005. The molarity was 0.1. So that's going to give you a moles of 0.0005. So that goes over here. And then I had nothing to start with of the ammonium. So the H plus is going to run out. We're going to make 0.0002 of the ammonium. So that's 0. This is 0.0003, 0.0002. Now look at what you have. You have NH3 and NH4 plus, which constitutes a buffer. So you're going to use the buffer shortcut. I'll use the OH1 since I know the KB. Alright, so KB, right over here, 1.8 times 10 to the minus fifth. Now we need the base, which is the 0.0003, over the acid, which is the 0.0002. And when you do the math for this, you're going to find the OH to be 0.00027. So that is the OH minus. So I'm going to do the POH, which is the negative log of that, equals 4.56. So then 14 minus 4.56 is going to give me 9.44 as the final pH. So if you want to draw a little picture of the final product here, you're going to have your cup, and inside your cup you're just going to have some NH3, and you're going to have some NH4 plus. And again, you formed a buffer by adding a strong acid in small amount into a larger amount of a weak base, and you turned some of the weak base into its conjugate acid, so you ended up with a buffer. On numbers 5 and 6, again, we're going to be adding HCl into each of these beakers, and remember that it's going to be 0.0002 moles that we're adding. Okay, in the first example, we had water, number 5. We ended up with water here, so we're going to add H plus to water, so clearly that's just going to be a strong acid. That's not going to be a reaction at all. So whenever you have a strong acid, you do molarity equals moles over liters. So you added 0.0002 moles into 10 milliliters altogether, which gives you a 0.02 molar of H plus. So when you take the negative log of H plus, you'll find out that your pH comes out to be the same answer that we got before, the negative log of 0.02. Let me just put that in here because I don't have that in front of me. 1.70. So 1.70 is the final pH, and that makes sense because it's acidic. Now we're going to move on to number 6. We're going to add H plus into our beaker, which let's redraw that here. We had a beaker that we created a buffer. The buffer had the weak acid HA, and it had the conjugate base A minus. So when you add H plus to this, the question is, will it react? And the answer is yes, stoic in moles. Anytime you add an acid or base to a buffer, it will react. So that's going to be yes, stoic in moles. And we forgot to circle buffer last time. All right, so we got to get moles here. And we're going to do H plus is going to find the base part of the buffer, which is the A minus. And that's going to form the HA, and we have to do this in moles. So we're going to do ICF. We're going to move this over so we have some room. Okay, we have to find the original moles of both the acetic acid and its conjugate base, the sodium acetate. So remember, originally, of the acetic acid, we had 0.1 molar, and the liters was 5 milliliters, so 0.05 liters. So that's 0.0. Oops, I did that wrong. That would be 50 milliliters if I wrote this. This has to be a 5, so 0.005. Gets confusing with all these zeros. That's why millimoles sometimes is nice. Alright, so this one's going to go 0.005 moles. So that's the moles of the HA. The original moles of the A minus is the same exact calculation because it was also a 0.1 molar and it was also 5 milliliters. So that's also a 0.0005 moles. Okay, so let's write all those in. I'm adding in 0.0002. Originally I had 0.0005, and originally I had 0.0005. So the H plus is going to run out, and I'm going to use that much of the A minus, make that much of the HA. So nothing of that. 0.0003, 0.0007. Now what do I have? I have a buffer. So I use the buffer shortcut. I'm just going to use the H plus since I know the KA. Alright, so I'll get that over here. K is 1.8 10 to the minus fifth. The acid is 0.0007. You can work in moles, of course. Base with the shortcut 0.0003. So when I do that, I'm going to find out that this answer is going to be 0.000042 molar. And that is the H plus. So I'm going to take the negative log of H plus. And I'm going to find a pH of 4.38, which is acidic, as you know. And this is going to be an acidic buffer. So when I'm all done, and I redraw the final product here, you notice that I had a buffer originally, right over here. I added H plus, and when I'm all done, I actually still have a buffer. So I did not wreck my buffer in this example. My final beaker is still going to have HA and A minus. We're now on numbers 7 and 8, where again we're adding HCl into each of these, but it's going to be the 0.0002 moles of HCl. So as we add HCl into this, it's a buffer. We ask ourselves, is there a reaction? The answer is yes. Remember, anytime you add an acid or base to a buffer, you will get a reaction. So we're going to do stoic in moles. So let's write the reaction. H plus is going to find the base part of the buffer. The base part of the buffer is NH3. And you're going to make the conjugate acid, which is NH4 plus. We're going to write ICF. This is 0.0002, what we added in. Now we have to find our original moles of each of the weak base and the weak conjugate acid. So we'll do that over here, just to give ourselves some room. We'll start with the NH3. Original NH3 is going to be 0.1 molar, and we took 5 milliliters of that. So that's going to be 0.0005 moles of that. The NH4 plus is the same exact calculation. I just want to show it in case you need help with that. So that's a 0.1 molar, 5 milliliters, also 0.0005 moles. So that's my original moles for that. That's my original moles for that. So I'm going to write it over here, 0.0005 and 0.0005. Now I'm going to run out of the H plus. So we're going to put the change line following the ratios. And when you're all done with this, you got no more H plus. You got 0.0003 moles of NH3. And you got 0.0007 moles of the NH4 plus. So now what do you have? You have a buffer. So to use the buffer shortcut, I'm going to take the OH shortcut since I know the KB. So that's going to be KB times B over A. So that's 1.8 10 to the minus fifth. Now I need the base. The base is the 0.003 divided by the acid, which is 0.0007. Okay, so on the calculator, I have to redo mine because I didn't write it correctly. This is going to be 1.8 times 10 to the negative fifth, and then we're going to multiply that by 3 and divide by 7 essentially. and that's going to give you 0.000. 0.000. Wow, it's a lot of them. 1, 2, 3, 4, 5 zeros. Again, millimoles. I guess that wouldn't have helped anyway. 7, and that's going to be your molarity of OH minus. Okay, that's your molarity of OH minus. And now you're going to take the negative log of that. Negative log of OH minus is going to be 5.11. Now that is the POH. So you're going to take 14 minus 5.11, and you're going to get 8.89. And that's your final pH. Now that's interesting because it changed pH a little more significantly, as you can see. 8.89, this started at 9.26. So it still didn't completely, change drastically, but there is a significant change in terms of a buffer there. So when you're all done with this, if you want to draw a quick picture of what you've got left, you still have a buffer. You still have a buffer, but the buffer is a little bit more acidic now because you added that HCl. So this is the NH3, and you still have NH4+. So you still have a buffer. You did not wreck your buffer. Okay, now we're going to move on to number 8. Number 8, again, is a buffer to start with, but it's an acid buffer. So you're going to add in H+, and you're going to ask yourself, is there a reaction? And of course the answer is yes. Whenever you add an acid or base into a buffer, it will react. So you're going to do stoic in moles. So put your H+ here, find the part of the buffer with which it reacts. It's going to be the conjugate base, and it's going to form the HA. And you have to work in moles, ICF 0.0002. Now we need the original moles of the A- and the HA, which we actually found already, so that's good news. See, this is the original moles of HA, 0.0005, and I'm sorry, well, when we made this buffer, we ended up with 0.00025 of the acid and 0.00025 of the base. This is where we're starting. Okay, so remember number 8 was originally I had a weak acid and I added OH minus into it, and I created a buffer. So I changed this into a buffer. So there's my buffer. This is the acid, this is the base. So that's my starting of my next part when I take H+ and add that into the buffer. So I'm going to write my moles here, 0.00025, and this is going to be 0.00025. And when we look at this, we're going to see that the H+ is going to run out. This is going to be minus 0.0002 plus 0.0002. So that's done. This is going to be 0.00005. And this is going to be 0.00045. And now we're going to realize that what do we have? We have a buffer. So we're going to do the buffer shortcut. So we're going to do the H+ shortcut, which is equal to Ka times A over B. And I'll give myself a little bit more space here. So we're going to go 1.8 times 10 to the minus 5th times the acid, which is the 0.00045, divided by the base, which is the 0.00005. And when you do the math for this, you should get H+ to equal 0.000162 molar. That is the H+ concentration. So when you take the negative log of H plus, you're going to get a pH of 3.79. Now let's look at this a little more carefully and understand. So first, we didn't wreck our buffer, which is good news, I guess, for a buffer. So you got HA and you got A minus. But look at this pH. This pH is 3.79. We started with a 4.74. So you can see that right here. So we changed by almost an entire pH unit, which is, kind of a large change for a buffer. But look at what happened. We were so close to wrecking our buffer. We added 0.002 of H plus, and we only had 0.0025 of the weak conjugate base. So you see how this is almost equal. We almost completely used up all our weak base of our buffer. So you could see how different these numbers are now than they used to be. They used to be equal. So the point is we're very close to wrecking our buffer when we added this much H plus. But we still maintained a fairly constant pH within 1 pH unit or so. Lastly, we're going to add HCl 0.0002 moles into number 9, which was a buffer, into here. So let's review what happened originally. Originally I had just NH3 in this cup and I added H plus. That reacted and formed a buffer. My buffer ended up with 0.25 millimoles of the NH3 and 0.25 millimoles of the NH4 plus. So now I have a buffer, and to this now established buffer I'm going to add more H plus, and we want to figure out what's going to happen. So we do realize that there will be a reaction, because anytime you add an acid or base into a buffer, it will react. So that's going to be yes, stoic in moles. So let's write the reaction. H plus is going to find the base, which is NH3, to form NH4 plus. So that's going to be ICF. Now I'm going to use millimoles. So 0.002 moles is the same thing as 0.2 millimoles. So I'm going to use 0.2 millimoles, and then I already knew my base, 0.25 millimoles. That was from over here. Okay, I made this, and then I also made 0.25 of the acid, so 0.25 millimoles of that. So we're going to run out of the H plus, minus 0.2 minus 0.2 plus 0.2. So when I'm all done with this, none of this is left. I only have 0.05 of this, and I have 0.45 of that. And now I'm going to use the buffer shortcut because I still have a buffer. So I'm going to use H, actually I'm going to use the OH because I know the KB. So KB times B over A. So that's going to be 1.8 times 10 to the minus fifth. I put the base on top, which is 0.05 millimoles. On the bottom, 0.45. And I do the math for this, and I should get 0.00002, and that's going to be the molarity of the OH minus. So I'm going to take the negative log of OH minus, and that's going to give me 5.70, but that's the POH. So then I'm going to take 14 minus 5.70, and I'm going to get my final answer of 8.30, which is the pH. So when I'm all done, I did not wreck my buffer. I still have NH3 in here, and I still have NH4 plus. But as we noticed in the last example, you'll see that the pH changed significantly for a buffer. It started at 9.26, and then it went to 8.30, which is almost a whole pH unit change. And you could see why, because you almost did wreck your buffer. See 0.2 and 0.25, you almost used all of this. You only have 0.05 millimoles left. So because you're almost wrecking your buffer, your pH is starting to change significantly, but still it's within 1 pH unit.